Topic of discussion for section 10.4 is area in polar coordinates. Before we get to area in polar coordinates, I just wanted to give everybody a quick reminder of how we came up with definite integrals for calculating area underneath curves in the first place. So we'll start with y as a function of x, like so, with an interval from a to b. To calculate the area under this curve, what we did is we broke this up into a bunch of little tiny subintervals, and on each subinterval we said we are going to approximate the area on each subinterval using a rectangle. The motivation for using a rectangle was actually twofold. A rectangle is quite easy to calculate in terms of its area. The area of each individual rectangle was simply a base times a height, or a length times a width. Now, the width of each of these rectangles we tried to keep as a nice consistent change in x, so we would call that delta x. And the length, or height, of each of these rectangles would depend on the value of x that we were plugging in from each interval. So we put an index on this to indicate all of the different intervals that we could be pulling from, and we used a star to say it doesn't necessarily have to be a consistent point from within the interval. There was the left-hand approximation, the right-hand approximation, the midpoint approximation. Ultimately, though, when we turned this into a limit, it didn't really matter. The important thing was, once we sum all of these individual rectangles and then allow the number of subintervals to go to infinity, it turns into a definite integral. The important thing is that the thing that we are integrating is, for all intents and purposes, the same as the setup of what we did for one individual rectangle. Now, we're going to do something similar, but this time we're going to do it for a polar curve. Now, for a polar curve, this is where we're going to be dealing with r's and thetas instead. Polar curves tend to be kind of round, so we're going to draw this thing here that's kind of round. We'll say that this is r as a function of theta. Now, up here we use two x values, a and b. Down here, we're going to use two theta values. We'll call them theta equals alpha and theta equals beta, the Greek equivalent of a and b. So what we're going to do is we're going to take this interval, we're going to break it up into a bunch of little tiny subintervals, like so. And on each of those subintervals, we're going to make an assumption about r, and the assumption we're going to make about r is that r is constant on each of these subintervals, which means that we are going to be approximating all of these areas using fragments of circles. These fragments of circles are referred to as sectors. I like to think of sectors as kind of like pieces of pizza that you would cut out of something that is round. The area of each of these individual sectors has a formula from back in pre-calculus, and the area of each sector is going to be 1/2 times r squared times theta, where r is going to be the distance from the pole out to each of these different radii that we're using, which is why I'm going to index the r and give it a star. Additionally, each of those little tiny intervals has a nice consistent value of theta, and it's actually going to be equal to a little tiny change in theta as we go from interval to interval. It is for that purpose that the area of this entire region can be approximated using all of these little sectors, but to find an exact value of the area, we would be integrating this. So add all of these individual sectors up, then allow the number of subintervals to go to infinity, and we wind up with the following definite integral. It'll be the definite integral from alpha to beta of 1/2 times r squared times d theta, where again, this part, the 1/2 r squared, is essentially the same, and the theta becomes a d theta. Additionally, because the integral is set up d theta, you'll need to make a substitution on your r squared to figure out exactly what is going on with that. So this is, the other stipulation here is that the upper bound minus the lower bound is going to have to be anywhere between 0 and 2 pi. Otherwise, you're talking about more than one full rotation around your polar curve, and that's just not going to work out. We will apply this formula to a couple examples in the next video. However, if we're going to talk about area in polar coordinates, another important topic of conversation is going to be the area between polar curves. Now for the area between the polar curves, that means we're going to have to define two different polar curves. We'll have an outer curve, r equals f of theta, and then an inner polar curve, where r is equal to g of theta. Now the reason that we talk about outer and inner is because outer is referring to a larger value of r, inner is referring to a smaller value of r. Again, r represents the distance from the pole out to each of these curves. Now, if we do the same thing as what we did on the previous example and break this up into a bunch of little tiny subintervals, then the areas in each of these subintervals can be approximated as a large sector minus a smaller sector. It is for that purpose that the area is going to be equal to the outer sector, so 1/2 of f of theta squared times whatever the change in theta is, minus 1/2 times the inner function squared, also times delta theta. Now we could factor out some greatest common factors, like the 1/2 that they have in common. So f of theta squared minus g of theta, also squared, times delta theta. Now, once again, we'll need to sum all of these up over all of the intervals, and then take a limit as n goes to infinity, and then poof, an integral. The total area is going to be equal to the definite integral from alpha to beta of 1/2 of your outer radius squared minus your inner radius squared d theta. And again, that's a formula we can use in a couple of examples in our next video.